The next thing that I want to talk about is the work done in a gravitational field. In the simplest possible case, we've already talked about this. We take an object that weighs 50 pounds, lift it 10 feet straight upwards. The work done is force times distance, 50 times 10, 500 foot-pounds. Except this isn't quite right. The force due to gravity is not a constant. To make this a little bit more clear, we need to talk about Newton's law of gravity. Newton's law of gravitation says that the gravitational force exerted on one object by another is proportional to the product of their masses and inversely proportional to the square of the distances between them. Calling the masses large M and little m, and the distance between the centers of the object, x, this says that there must be a constant g so that the force is this constant g times the product of the two masses divided by the inverse square of the distance between them. That is to say, F is g times capital M times little m over x squared. In meter kilogram second units, the g is approximately 6.67 times 10 to the negative 11 power, although as we will see, in many applications we don't explicitly need to know what the g is. The radius of the Earth is about 6.4 times 10 to the 6 meters, which is about 4,000 miles. The mass of the Earth, if we need to know it, is about 5.98 times 10 to the 24 power kilogram. So I want to imagine that I have an object that weighs 100 pounds on the surface of the Earth, which is about 4,000 miles from the center. X would be 4,000 miles. I'm going to lift the object upwards until it's 8,000 miles from the center of the Earth, meaning that it's 4,000 miles from the surface. I want to think about two questions. Firstly, what is the object going to weigh at the 8,000 pound distance, and how much work was required to move it there? At x equals 4,000, the force is 100. I have to keep in mind my distances are in miles and my weight or force is in pounds. This is very similar to what went on with Hooke's law. By telling you that the force is 100 when x is 4,000, knowing Newton's law of gravitation, this will let us figure out what the constant k is. I'm still going to write the quantity with the letter k, but in point of fact, we know what k is. It's 100 times 4,000 squared. I'll just write that in when I need to use it. Just as with the Hooke's law problem that we've previously looked at, the amount of work needed to do this is going to be the integral of the force with respect to the variable that tells me where I'm at, the x in this case. One little point, x does not start at 0. X starts at 4,000 and ends at 8,000. This will be important to take note of when we calculate the work. To calculate the weight at 8,000 miles from the center, though, is easy. If you moved to x equal 8,000 miles and were held stationary there by some rocket engine firing, for instance, then in that situation the object would now weigh only 25 pounds. It still has the same amount of matter that it used to, the same amount of mass, but the response to gravity is weaker because of Newton's inverse square law. The reason that astronauts don't feel gravity is not because they've escaped from it. When you're in orbit, you and whatever craft you're in are in free fall. You are falling at the same rate. This is why you don't feel the acceleration due to gravity. It's a generic result that the work is the integral of the force with respect to the variable that tells me location. For Hooke's law, the force was some constant times x. For gravity, it's some constant divided by x squared, where x here represents the distance from the center of the Earth. Putting the numbers into the calculator, I find out that the amount of work needed is 200,000. Now, since work is in distance times force, I'm measuring my forces in pounds and my distances in miles. This is 200,000 mile-pounds. If I want to convert this into foot-pounds, I have to remember that every mile consists of 5,280 feet. I would need to multiply this by 5,280. This turns out to be just a little above 1,000,000,000 foot-pounds, so it would take a very large amount of energy to do this. I want to contrast the difference between mass and weight. Weight is the response to gravitational fields. Weight is a force. On the other hand, mass is a measure of the amount of matter that's in an object. So if I take an object on the surface of the Earth, it has a certain weight, and it also has a certain mass. If you were to move this a great distance away from the center of the Earth, the mass would be the same, the amount of material, but the weight, the force, would be different. If I want to work directly with the masses, then I do have to know about that G constant, the one that's about 6.67 times 10 to the minus 11 in meter kilogram second units. I want to think about this situation. I'm going to start off on the surface of the Earth at r sub e. This is 4,000 miles roughly, about 6.4 times 10 to the 6 meters. I want to raise the object up until it is a distance of b meters from the center of the Earth. Based on our previous ideas, the amount of work is the integral of the force with respect to location, starting at the surface of the Earth. That'll be x equal r sub e, ending at x equals b. This formula is a relationship between how much work needs to be supplied to move an object a distance b from the center of the Earth. A very interesting feature of this equation is if you let the b become indefinitely large, the second term tends to 0. I'll call the limit the escape work. If you give the object an amount of energy, G capital M, little m over the radius of the Earth, then the object will move arbitrarily far away from the Earth. In a certain sense, it will escape. It will go up, but it doesn't come down. I could give it this amount of energy or work in a variety of ways. I could take the object and lift it 1 meter upwards, hold it there for a while, lift it another meter upwards, hold it there for a while, and then repeat. That would take, in practical terms though, a tremendous amount of rocket fuel to do. So instead, what people tend to do is they supply the object with this amount of work in one big push during a very brief period of time. They give the object this amount of kinetic energy. The kinetic energy of an object is 1/2 of its mass times the square of its speed. So if I want to escape, then what I need to have is this. The kinetic energy of the object equaling the escape energy means that 1/2 little m v squared needs to be g capital M little m over the radius of the Earth. This is easy to solve for v in terms of all the other quantities. A noteworthy fact is that little m cancels out on both sides of the equation. Starting at the surface of the Earth, if an object is hurled upward with this amount of speed, this amount of velocity, then it will escape. For that reason, we call this number the escape velocity, and since we know Newton's constant, the mass of the Earth and the radius of the Earth, we can actually calculate it from this formula. I need to calculate 2 multiplied by 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 divided by 6.4 times 10 to the 6, and having obtained that number, take its square root, which of course is the same thing as raising a number to the 1/2 power. This number is about 11,164 meters per second. I haven't bothered writing all the other digits down because my constants were all given only to 2 or 3 significant figures anyway. This is in somewhat unfamiliar units. There are about 1,609 meters in a mile, so every meter is 1 over 1,609 of a mile. There's 3,600 seconds in an hour, so each second is 1 over 3,600th of an hour. I can use those facts to convert this into miles per hour. So I'll have an additional factor of 1 over 1,609 divided by 1 over 3,600. That is to say, I'll have an additional factor of 3,600 over 1,609. Using the available information, that would be 24,979 miles per hour. This is escape velocity from the surface of the Earth or near the surface of the Earth. Usually in books and articles, people just quote a figure of 25,000 miles per hour. This is where that figure comes from. This has been the second of our 3 types of work problems that we'll look at. Coming up soon, work done by an expanding gas. I hope everyone's having a good day. I'll talk to you again soon.